Okay, this right here is the Jacobi theta function. It's not the theta function that you would expect in most other circumstances, right? That theta function has two inputs and it's a lot more flexible than this. Instead, this is a very specific case of that function, right? That we use in analytic number theory, but we still call it the theta function. Why is it useful? Well, it's because of its functional equation, which I wrote down in red right here, yeah? And I've used this functional equation before in a few of my videos. One of which is the functional equation of the Riemann zeta function, right? I leveraged this property before, but I never bothered to prove it. So today I'm going to prove this. One of the tools that we're going to be using is this thing I wrote down in red up here. And that's called the Poisson summation formula, right? So the left-hand side of this guy right here is kind of similar to, no, it's basically the same as what we have on here. This right here is going to be our f of n, okay? And it's equal to this whole thing right here. It's just the sum going over all of the integers of the Fourier transform of f, okay? So let's work this out. So if this is the left-hand side, then the right-hand side, I'm going to copy this down. It's going to be the sum going from k equals negative infinity up to k equals infinity. And then we have this integral bar right here that also goes from negative infinity to infinity. You have f, but now the function is t, right? No, f, but now the variable is t. So this is our f, right? E to the negative n squared pi x, but this is f of n. That's f of t. I'm going to take all the n's inside of here and replace it with a t. So instead of n squared, we now have t squared. It's the exact same function, right? It's just we called the variable something slightly different. Okay, and then the rest of this. E to the negative 2 pi I k t dt. Okay, so now let's go ahead and work on this integral. So what are some steps we can do to simplify it? Well, notice that it's just two exponentials, right? So I'm going to copy this down. Well, we can go ahead and combine the powers. So we're going to have e of this guy right here plus that guy right there. But before we write that down, we can actually factor some stuff out, right? Notice how we have this negative sign in both of them? We also have a pi in both of them. And I'm not going to factor out a t. So we're going to just copy the rest down, right? And this one, after factoring out a negative sign and a pi, you still have 2 I k t. And then dt. So what's nice about this is that now you almost have a quadratic, right? You can make a substitution to make it look perfectly like a quadratic. If you just made this guy like u squared, right? Then this would be something you could complete the square for, which is something that we're going to do next. So let's do this first, right? Let's let t squared x equal to u squared. More specifically, if we wanted to isolate t, right, because we don't know what t is by itself, then t is equal to, well, you'd have to divide x on both sides, right, and then take the square root. So on the top, you end up with u, right, the square root of u squared is u, and then you divide it by x on both sides, so now there's an x in the denominator, except you took the square root, right, to get rid of the square on the t, so now you have a square root on top of the x, right? Okay, so we have this. Let's differentiate both sides just to find the differential element, right? What is dt equal to, basically? And on the right-hand side, the derivative of u is just du. And then the root x is actually just a constant, because our integral is in terms of t and in terms of u, right? Not in terms of x. What about the bounds? Well, notice here that t, when t is equal to negative infinity, u should also go to negative infinity, right? Because this guy right here, this root x, is never going to be a negative number. Yeah, you can all agree on that. And then same deal when it goes to positive infinity. When t is positive infinity, then u also has to go to a positive infinity. Okay, so our new integral is, well, I'm going to copy the sum down that goes on the outside first. K equals negative infinity to infinity. Okay, our new integral, the bounds are going to stay the same, right? So it's still negative infinity up to infinity. We have this e to the negative pi, that doesn't quite change. But now, notice that this t squared x it's just going to become a u squared. We have plus 2ik, none of that is affected. Okay, this t we're going to have to write in terms of u, and that's right here. So t is just u over root x. So I'm going to write this as 1 over root x times u, okay? And I'm going to close the parentheses. And then finally we have dt, which we saw is just du over root x. So let's put that down. Okay, so we have that, yeah? Move this back up a little bit. Okay. So now, what can we do? Well, first notice that this root x, right, is independent of everything, yeah? This integral on the inside is in terms of u, but root x, 1 over root x, is kind of just a constant in terms of u, so we can move that outside. We can also move it outside the sum, because this sum, well, 1 over root x is independent of k, which is the index variable for this sum. So, we could just move the 1 over root x way out to the outside. So you can kind of see this 1 over root x pop out. Now we just have to prove that the rest is equal to this theta, of 1 over x. So we still have the sum that goes over the integers. I'm going to just write it like this, right? K equals negative infinity to infinity. Same thing as saying sum k over all of the integers. Then we have the integral over the real numbers, right? Negative infinity to infinity. On the inside, we still have that. But now I'm going to complete the square. So we have u squared plus 2ik, 1 over root x times u. Okay, now we want to add and subtract a number that makes it a perfect square. So what number would that be? Well, we know that that number is just, we take it, right? Take this coefficient right here, and then divide it by 2. So this guy divided by 2, this 2 is just going to disappear. We have ik times 1 over root x. And then we square the whole thing, yeah? So what is this now? I squared is just a negative number, right? Sorry, negative 1. And then k squared. And then 1 over root x squared is just over x. So the number that we subtract off is k squared over x. So these three terms now is a perfect square trinomial. We can rewrite it as something plus another thing all squared. But we subtracted this, right? To keep the value of the exponent the same, we have to add it back, right? So we have this other k squared over x that's just hanging out up here. Okay. And then we have our differential element du hanging out on the side. I'm going to rewrite this guy now. So copying all this down. Okay, so these three terms, how do we write it as something squared, right? Well, the first term is obviously going to be u. And then the second term is always just going to be this middle guy right here, divided by 2, right? And in this case, we add it. Add this guy divided by 2, we just get ik over square root of x. Okay, and that's squared. So that's these three terms taken care of. We still have this last term back here, so I'm just going to tack that on. Okay, and then du. Okay, now we can make another substitution, but before we do that, this pi out here is also kind of annoying. I'm going to drag it to the inside and distribute it among these two terms, yeah? So let's distribute, okay, well, let me copy this down first. We have this e, and then we have the negative sign, but I'm going to distribute this pi to the inside, right? When it gets inside of this guy right here, pi times this squared guy right here, well, we can rewrite as a root pi times whatever's on the inside, right? And then everything squared. Because what happens is the square distributes onto this factor, right? So we get this back, but also this root pi right here. So we get this pi out again, okay? So this is exactly what I'm going to rewrite. Root pi times u plus ik over root x. And then all of this squared, okay? This pi also distributes onto this other term right here. So k squared pi over x. All right, nice. So we now got rid of that pi. Now it's part of these guys. First of all, notice that if you just go ahead and distribute this negative sign right here, so it's going to look like this, right? Just take this negative sign and multiply it into both of those terms. We get that. This e to the negative k squared pi over x is independent of u, right? Our variable integration. So we can go ahead and take that outside. So we have this 1 over root x, and then this sum over k goes over the integers. We have this e to the negative k squared pi over x. Okay, but we still have this integral on the inside, going from negative infinity to infinity of e to the negative, and then inside we have, there's a parentheses there, root pi times u plus ik over root x squared, and then we have this du at the end there. Okay, now this almost looks like something very familiar, the Gaussian integral, right? If you remember, the integral going from negative infinity to infinity of e to the negative x squared dx is simply equal to square root of pi. So if we can get this guy in that form, then, we're home free. So basically, only thing that is different between these two is that this guy is a whole bunch of crap, and this guy is not, right? That's just a single variable, this is not. So I just want to make a substitution, right? Maybe let's use alpha. Alpha equal to root pi times u plus ik over square root of x, right? So that way, everything that's going on inside of this square right here is just going to be a singular variable. So it's going to look just like that. Okay, first of all, I'm going to move this back up. Okay, so first, in this substitution, let's put down the bounds first, so the bounds are basically unaffected, right? If u goes to negative infinity, then negative infinity plus something, that's not going to really change the value. Multiplied by root pi, that's also not going to change the value, right? Infinity plus or minus anything is still infinity. And then multiplying by a finite number is also going to remain infinity. So that's true for both the top bound and the bottom bound, right? So it still goes from negative infinity up to infinity. On the inside, e to the negative, well, this whole thing we literally just called alpha, right? So we now have alpha, and then it has the square that's tacked on top. Now we got to find du, right? So how do we do that? Well, let's go ahead and first divide root pi on both sides, right? So alpha over root pi equals u plus ik over root x. Now we can go ahead and differentiate both sides. On the left-hand side, this root pi, it's just a constant, right? So I'm going to leave it in the denominator, and then the derivative of alpha is just d alpha. On the right-hand side, this second term right here is just a constant. So when we take the derivative, it's going to go away. All we're left with is the derivative of u, or the differential of u, right? du. So du is just d alpha over root pi. And we are almost done, because we now know that the value of this integral right here is just square root of pi. So I'm going to copy this all down again, 1 over root x times the sum, as k goes over the integers, of e to the negative k squared pi over x. This integral evaluates to square root of pi, right? But notice that we have this constant factor of root pi in the denominator too, so that's still going to be there. So these eyes are going to just cancel out. So all you're left with is this, right? After applying this Poisson summation formula, you went from this left-hand side to the right-hand side, but concluded that it looks like that now. Okay. Well, this looks just like the Jacobi theta function, right? At least this sum right here does. So this 1 over root x is going to stay on the outside, but this guy is some sort of Jacobi theta function. We can move this over x to the side as 1 over x, right? And notice now that this sum right here looks exactly like this sum. But instead of an x, Here, we have 1 over x. So, this is not the Jacobi theta function of just x, it is the Jacobi theta function of 1 over x. So there you go. After applying this Poisson summation formula to this starting function right here, we achieved this form, right? Slightly different, but we rewrote it in terms of the theta function, and that's where we get it from, right? This is the left-hand side, theta of x, and this is the right-hand side. So we just proved that this guy right here is true.